One of the hardest parts for IB math students when dealing with optimization problems is how to assess whether you or the student got a max or a min after arriving at a critical point. So the process of finding maxes and mins, which means optimizing a given model, is the same. We take the first derivative, we equal it to 0. However, we need a technique, we need a test to assess whether we get a max or a min. And there are two routes that we can use, either the first derivative test or the second derivative test. Each one of these has their own advantages, provided some specific criteria. In a nutshell, when your second derivative is very easy to calculate, we usually use the second derivative test. However, if differentiating again is a problem, is an issue, then we usually stick to the first derivative test. In this exercise right here that you see in your screen, we're going to go through, well, this optimization exercise, which is not trivial. And towards the end, we're going to assess whether we actually got a min by using the first derivative test. So let's get to it. We have a piece of wire of total length capital L, which is a constant, and that piece of wire is cut into two parts. One part is used to form a square, and the other one is used to form a circle. So let's create a little sketch for that. Let's say that this is our piece of wire. This piece of wire has length L, and we are going to cut it in order to use part of this piece of wire to form a circle. So let's call this lowercase x, and the other part, it is used to form a square. So this is L minus x. We don't know exactly what x will be. That's exactly the purpose of this question. However, we can safely assume that x will be a fraction of L. Now let's create a little diagram here in order to represent the square and the circle. If we're going to use the length L minus x to form the square, and given that squares have 4 equal sides, each side of this square will have a length of L minus x over 4, which means that its area, let's call this A2, it is equal to L minus x over 4 squared. Now for the circle, it's a bit different. We have the circumference, which is x. We have x amount of wire to form the circumference, which means that given the circumference is 2 pi r, the radius is x over 2 pi, which means that this A1, area 1, is pi times r squared, which means pi times x over 2 pi squared, which we can simplify a bit to x squared over 4 pi. Now, knowing how to solve optimization problems is knowing how to answer these questions. So first of all, understand the problem. What was given? What are we trying to optimize for? We're trying to minimize the total area, which means that if we call the total area capital A, it will be equal to L minus x over 4 squared plus x squared over 4 pi. So we can write this function as a of x, given that x is the variable right here. Now, other questions that we either answered already or we still need to think about are, number 2, sketching was done, our sketch is done. We did attribute variables to the quantity, so we have capital L as the total length of the wire. We have x as the fraction of the wire, which is going to be used in the circle. We have areas being represented as capital A. We already dealt with the restriction, which is capital L. It's a finite amount of wire. And we just defined the function to be optimized. We did write it in terms of one variable only, which is lowercase x. The next step is to find the critical points, which means that we need to differentiate a and equal it to 0 to find our critical point x equals something. We're going to see what that something is in a minute. But first of all, what is a prime of x? Before differentiating a of x, you can rewrite a of x as such. This is the same as L minus x over 16, and this L minus x is squared. And this can be represented as 1 over 4 pi times x squared. Now, on the second term, I deliberately separated the 1 over 4 pi from the x squared to make it very evident that 1 over 4 pi is just a constant. And you can do the same right here. This is 1 over 16, L minus x squared, plus 1 over 4 pi times x squared, which means that the derivative of a is 1 over 16 times the derivative of L minus x squared, which by using the chain rule gives us 2L minus x to the first power times the derivative of negative x, which is -1. This can be rewritten, of course, as -2L minus x, which means that we have over here -2L minus x plus 1 over 4 pi times the derivative of x squared, which is 2x. We're going to take this and equal it to 0. So we have -1 over 8 multiplying the 2 and the 1 over 16, L minus x plus x over 2 pi, which is equal to 0. Now, we can rewrite it as x over 2 pi equal to 1 over 8 L minus x. We can cross multiply the 8 and cross multiply the 2 pi, which gives us 8x equal to 2 pi L minus x. So 8x is equal to 2 pi L minus 2 pi x, which means that 8x plus 2 pi x is equal to 2 pi L. We can divide everything by 2 and factor out an x on the left hand side. So we have 4 plus pi times x equal to pi L, which means, and right now this is our critical point, x is equal to pi times L over 4 plus pi. Now, as I mentioned before, this answer should be a fraction of L. That's the only way that this exercise would make sense. And it is, if you think about the constant, which is multiplying capital L, which is pi over 4 plus pi, given that you could rewrite this x as pi over 4 plus pi times capital L. This number right here is less than 1, which means that x is a fraction of L. Now, the million-dollar question is, does this critical point provide us with a max area, the area composed of these two shapes, or does this critical point provide us with the minimum area, which is exactly what we want? Now, in order to test it, we can either use the first or the second derivative tests. In this case, we're going to use the first derivative test. And how does it work? We're going to draw a number line placing the critical point over here, and this number line represents the derivative, so a prime of x. And by the way, it's worth mentioning that a prime of x is this, as found before. So we're going to place a prime of x over here. And we're going to use one x value for each one of these intervals. We have two different intervals from -infinity to pi L over 4 plus pi, and from pi L to over 4 plus pi to positive infinity. So we might use here, for example, L over 10, which is smaller than pi L over 4 plus pi. And we also may use 2L for the interval on the right. And we are going to replace these numbers in the equation or in the function a prime of x. Why do we do that for? We test the sign of the derivative, placing those values into the derivative. So that's going to tell us whether the function is increasing or decreasing. So for example, for L over 10, a prime of L over 10 is -1 over 8 L minus L over 10 plus L over 10 over 2 pi. Given that this is 9L over 10 and this is L over 20 pi, and we can rewrite this as -9L over 80, we have L times -9 over 80 plus 1 over 20 pi. Now, L is a positive constant. We just need to ask ourselves whether -9 over 80 plus 1 over 20 pi is positive or negative. Now, given that this is approximately -0.0966, a prime of L over 10 is negative, which means that the function is decreasing in this interval right here. If you replace your x value by 2L, you get -L over here and L over pi right here. And both of these terms, they're positive. Therefore, the function is increasing in this interval right here from pi L over 4 plus pi all the way to positive infinity, which means, and now using the first derivative test, if f prime changes from, it's actually this line, changes from negative to positive at the critical point, that means that over here at pi L over 4 plus pi, we have a local minimum point. And this is exactly what you need to write. Given that the sign of the derivative changed from negative to positive around x equals c, x equal the critical point, which means x equals pi L over 4 plus pi, we have a local minimum when x is equal to pi L over 4 plus pi. Now, can I use the second derivative test? Yes, for sure you can, and it's actually quite fast to do that. But do know that if you differentiate it again, you will get a second derivative, which is not actually a function of x. It's just 1 over 8 plus 1 over 2 pi, which is not a problem at all. What it shows us is that this second derivative is positive. And if you use the second derivative test, you know that when the second derivative is positive at the critical point, that means that we have a min over there. So that's it.